Okay, the title of my talk is Trojan Wave Packets in the circularly polarized and the magnetic fields on the multi-layer Langmuir type 1 helium trajectories extended for odd number of electron atoms. So let me make a brief introduction. What is the Trojan wave packet? So imagine you have a hydrogen atom in the circularly polarized electromagnetic field in the dipole approximation. When the electric field vector is rotating in the plane, and this kind of field conditions can generate solitonic solutions of the probability density of the electron in the hydrogen atom. So this is a picture of the Trojan wave packet in the rotating frame or at the fixed time in the laboratory frame for quantum state, which is localized in the spectral space around principal quantum number 60, and then the frequency is 1/60 to power 3. And you can see that there is a Gaussian solitonic shape, and in the laboratory frame, the packet is moving on a circle, so it is rotating around the nucleus in the center, and it is a soliton of the probability density of the electron in the hydrogen atom. So in some sense, it corresponds to the Bohr atom. Okay, so let me revise a simple theory of it, and the theory actually was not so simple when we were generating it, but now in the context of from a time perspective and in the context of other problems, we see that this is a Stark-Zeeman problem. We have the Hamiltonian in the rotating frame has a Stark term, and the incomplete Zeeman term, which is simply omega LZ. And what you can do is that if you solve the Schrödinger equation in the basis of the hydrogen eigenstates, then you will find out that there is one specific state per millions, one specific state which looks like a Gaussian. And the reason of that is that effective Hamiltonian, which you can construct in the sector of the states with fixed deviation from circularity, which is the difference between the principal quantum number n and L, and difference between principal quantum number n and L and M. Okay, so these are fixed deviations from circularity with tilt. You consider deviation in quantum number m, and then you will find out that if the deviation is minimal, which is that L is equal n-1 and M is equal L, then you will find out that you can construct the Gaussian state, and the reason of that is that the Hamiltonian is pendular, and what is so interesting here that the pendulum has the negative mass. Okay, so now you can also explain the localization, Gaussian localization around the circular trajectory and around the point in the rotating frame, and the motion around circular trajectory within the harmonic approximation, that you expand the Hamiltonian up to second order, and then you have this is the stability plot, when these are the coefficients of the harmonic oscillator. So you see that the saddle point corresponds to the case when the n coefficient is negative and the second is positive, and this the black line is the constraint, which is the equilibrium point. You will find out that the crossing the constraint with the stability zone is generating the zones when the packet is stable and Gaussian. Okay, so now what you can do, the first thing you can do is to try to extend it to 2 electrons, and this is page from the Irving Langmuir paper from 21, when they were trying, he was trying to quantize helium, and you see that he found the two electron trajectories when electron 1 is moving on circle, electron 2 is moving also on a circle, and the nucleus is symmetrically in between. So what we did first, this is the Langmuir helium again written down, and you will find out that you can find out analytically the solutions for the fixed frequency. You can find in analogy to the Bohr atom, you can find the radius of motion, and also you can find the distance between the plane of the motion of one electron and the second symmetrically with respect to nucleus analytically. Okay. And what we did first is we put this atom, this Langmuir trajectories in the external magnetic and electric fields, and we found out that they can be stabilized. This is the classical stability analysis when you consider small deviations from the circular trajectories or simply from the fixed point in the rotating frame. This is general stability analysis of the for n electrons. So you are getting problems similar to finding the band structure. So in solids, when the number of the bands is basically 6 times n, when n is the number of electrons. Okay, so if you perturb slightly Langmuir trajectories without fields, they are unstable. They finally they will be completely destroyed on small perturbation. This perturbation is growing, and what happens is now here that if you put external electric field and the external magnetic field, this is in units when the cyclotron frequency of the magnetic field is either plus or minus 1, you will find exotic stability zones when the motion is either stable or unstable, and the stable motion is corresponding to the Gaussian 2-electron wave packets. So now if you plot probability density, you have 2 Gaussians moving along the trajectories in the stability zones. So these are quantum diffusion Monte Carlo simulations when the wave function is of this Langmuir stabilized helium, when the wave function is represented by the density of points or walkers, the wave function itself, not the probability density. So now you will find out that if you have n electrons, you can have so-called allotropes of the electron Wigner molecules. So you can have many configurations which are stable, which are fixed, not moving in the rotating frame. And if the gradient, if the folding, the number of times the line is crossing the gradient of the zero velocity surface is at least 2, non-trivial is 2, because one is it is 1 for plane, then you will find out that you can have 2 to power 3n possible configurations in principle. For example, for 60 electrons, you have 180. And here is an example on the 3 ellipsoids. When the 3 ellipsoids are crossing with Dewar ZVS, zero velocity surfaces, there is 8 crossing points between 3 ellipsoids. So now, for example, if you have 10 electrons in plane, this is distortion by the electric field. If you put electric field around, the configuration is changing, is distorted. And you will find out that if you make cumulative plot with many fields, many electric and magnetic fields, you get some interesting sun shape, and also very exotic. Similarly to the 2-electron case, the original one, above 1 electron, you get exotic stability zones when they are the blue regions are the most stable motion, and they are much more complicated for 2 electrons. And now we want to extend it for n electrons, and for even number of electrons, it is quite simple, because you simply separate electrons into 2 sets, and one set is you place electrons of n-gonal prism. And they are the whole thing is rotating. Okay, when you add the magnetic field and electric field, of course the radius of the motion is changing on the magnetic field, and the electric field which is rotating is causing the shape distortion, shape distortion. So the original shape is slightly of n-gonal prism is slightly deformed on the external field. And to the case I'm discussing here, that if you have an odd number of electrons, then you basically factorize the number of electrons. You find divisors of this number, and for example, for 15 electrons, you have 3 layers of electrons, and that now both blue balls and the green balls, both blue balls and the green balls are also electrons, and the red ball is the nucleus again. This can be either the number of electrons may be the charge may be the atom, or they may be an ion, may be excess. Okay. So let me go how you can confirm them numerically. So the only way to run the simulations on the grid is the time-dependent Hartree-Fock approximation when you consider n single electrons equations, and each electron is in the effective field of other electrons, and then therefore the field of the other electrons plus the magnetic field plus the rotating electric field are creating conditions suitable for the non-dispersing wave packets. Okay. So this is how the diffusion Monte Carlo simulations look. You have this is for even number of electrons, 12 for example, and this is for odd number of electrons, 15. So you see the wave functions are dispersed because there is a probability density, and you have 3 layers of you can confirm exactly in the sense that you solve exact Schrödinger equation for n electrons. You can only use the quantum diffusion Monte Carlo, either static in some cases or time dependent, which we developed recently. I developed recently the time dependent extension of the quantum Monte Carlo method with color walkers. Which walkers have features, and they interact, annihilate each other, or so on. And you can confirm this only exactly in the sense that you solve exact many-body Schrödinger equation only in time-dependent Monte Carlo simulations, because otherwise on grid you have to use mean field. So in summary, in 1921, in Langmuir, in early attempts of the quantization of the helium atom by the Bohr-Sommerfeld conditions, found the periodic, the parallel circular 2-electron classical trajectories in the, I call it Hoopi ring configurations, because they resemble Hoopi rings. Okay, the trajectories are always unstable, can be stabilized by the combination of the symmetry augmented magnetic and the electromagnetic circularly polarized CP fields. We find such trajectories now to be possible for both even 2n electrons and odd 2n plus 1 electrons, and electrons with each m of the electrons placed on the vertices of the rotating pairwise identical regular polygons symmetrically placed with respect to the central polygon, all embedded in L parallel planes, which can be stabilized by the external fields, like in the case of 2 electrons, and the external rotating field is breaking the discrete rotational symmetry of the rotating prism, which is built from n-1 and gonal frusta. Okay, or twisted variation, because you can phase shift the neighboring ones, and you have twisted version of this by preserving its original nature, causing the distortion, and such trajectories can support stable stable non-dispersing multi-electron quantum wave packets with the probability density of the rotating Wigner crystal electron molecule with the same symmetry, and they can be confirmed with the either Hartree-Fock three-dimensional grid simulations, which is mean field method, or in the Hartree limit, or with stationary on our recently developed new time-dependent quantum diffusion Monte Carlo method. So now I will stop.